As an example, let's calculate the thermal efficiency of a power cycle. This calculation is relatively straightforward, so really this is practice in becoming accustomed to the sign conventions associated with cycles. We've spent a few weeks making sure that we get the sign conventions right for energy conservation, and now we have to throw that out the window just temporarily, so good to understand how it works. Let's say that we're given that a power cycle performs 100 kilojoules of work and outputs 80 kilojoules of heat. What is its thermal efficiency? And you may expect to be given problems like this where all of the givens are stated in words. Well, the first thing we ought to do is be able to represent a power cycle. So from your lecture notes or from the book, you can see that a power cycle is something like this, where work goes out, you get energy in from the hot reservoir, and energy goes out to the cold reservoir. So it's this detail, the subscript cycle or the subscripts in and out, that tell you that all of these quantities that I've drawn here, W and the two Q's, are going to be positive. Now, of course, we can't change the fact that in the energy conservation law, certainly W and Q potentially have signs, and you still have to do that self-consistently. But when we're computing an efficiency, the important thing is that you remember all of these are positive. So we would say that W cycle is 100 kilojoules, and that Q out is 80 kilojoules. So those are our givens. And again, I just wanted to write that out explicitly to make sure that we're okay with the sign conventions here. Okay, so now let's go through and compute this thermal efficiency. Well, eta, the thermal efficiency for a power cycle, is the work done by the cycle divided by Q in. And if you'll recall, for a power cycle, this has to be greater than 0 or less than 1. And for a power cycle, we know the relationship between W cycle, Q in, and Q out. So it's simply that W cycle equals Q in minus Q out. And I put that greater than 0 over on the right-hand side. That's there to remind us that since Q in and Q out are both greater than 0, they're both positive, it must be the case that Q in is greater than Q out. Okay, so we can rearrange this to solve for Q in, which is what we need in the expression for eta, so it just equals W cycle plus Q out. Now we plug that result into our expression for eta, and now we can just put in numbers. So W cycle is 100, Q out was 80, both positive, and that gives us an efficiency of 0.56, or 56%, it's equivalent. That number may not mean a whole lot now. Generally, it's used to compare different power cycles to see which are the most or least efficient. Likewise, eventually in this course, we'll come up with expressions that tell us the maximum theoretical efficiency for power cycles, and we could potentially compare an actual power cycle efficiency to this theoretical maximum just to see how well we're doing.